When you multiply a whole number with the exact same whole number, what you get is a perfect square. If you consider the numbers from 1 to 100, these are the perfect square numbers. 1 into 1 is 1. 2 into 2 is 4. 3 squared is 9. 4 squared is 16, and so on. These are some more perfect square numbers. These numbers are called as perfect square numbers because they can be arranged as a square, a perfect square. Let's consider a few of them. We can arrange 10 dots as a row and take 10 such rows to form a square. This will have a total of 100 dots. We can also do this for 9 square. 9 dots in a row and 9 rows arranged as a square. A total of 81 squares. 8 into 8, we have 64 squares. Similarly, we have 7 square, which is 49, 6 square, which is 36, 5 square, 25, 4 squared, 16, 3 squared, 9, and 2 square, 4. Next, let's learn if a given number is a perfect square number. For example, 784. We'll first use the prime factorization method. Using this method, these are the factors of 784. Now, let's group these factors to similar pairs. 2 into 2, 2 into 2, and 7 into 7. This becomes 2 square, this is 2 square, and this is 7 square. Now, this expression can be written as 2 into 2 into 7, the whole square, which is 28 squared. In simple words, for every pair of similar factors, we take only one of them and find the product. Here, we can say 28 squared is 784, or we could also say that square root of 784 is 28. Now let's check if this number is a perfect square. Let's start with prime factorization. So these are the factors. All of them are paired. So it is a perfect square number. So to find the square root, let's consider one among the similar pair. So we have 2 into 7 into 5 into 2, which is 140. So we can say that 19,600 is 140 square, or the square root of 19,600 is 140. Now let's try to solve this question. Find the smallest number by which 4,851 must be multiplied to get a perfect square. As usual, we'll start with prime factorization. Here we can see that we have a pair of 3 and a pair of 7. But 11 is only a single factor. So this number 4,851 is not a perfect square number. To make it a perfect square, we can multiply this number with 11, in which case a pair of 11 will also be the factors. And what results is 3 into 7 into 11, the whole square, which is a perfect square. So the answer for our question is 11. Another similar problem. Find the smallest number by which 28,812 must be divided to get a perfect square. On doing prime factorization and finding the factors, we have pairs of 2, 7 and 7. But 3 is a single factor. So again, this number 28,812 is not a perfect square. To make it one, you have to either multiply it by 3 or you could also divide it by 3. From our question, we are concerned only about division. So we'll divide this number by 3 to make it a perfect square. 2 into 7 into 7, the whole square. So our answer is 3. Now we'll move on to properties of perfect square numbers. These are all the properties of perfect square numbers. Let's check them one by one. First, a perfect square number cannot end with 2, 3, 7 or 8. To understand this, let's check the list of squares of the numbers from 1 to 10. We are concerned only about the ending digit. Here we can see that the numbers 1 square and 9 square end in a 1. 2 square and 8 square end in 4. 3 square and 7 square end in 9. 4 square and 6 square have 6 as the ending digit. 5 square has the digit 5 and 10 square has the digit 0. So if you take the digits from 0 to 9, these were the ending digits of the perfect square numbers. If you calculate further perfect square numbers, you can find that the same pattern continues. So this means the perfect square number will never end with the remaining numbers 2, 3, 7 or 8. Using this understanding, from these numbers, let's identify the numbers that cannot be perfect squares. The option B, 752, ends in a 2. And the option D, 418, ends with 8. So these two numbers cannot be perfect square numbers. Another important point to note is that all the numbers that end with 0, 1, 4, 5, 6 or 9 are not always perfect squares. For example, 14, 19 and 10. Though the ending digits are satisfying the condition, they are still not perfect square numbers. The next property. If a perfect square number ends with a 0, it should always have an even number of zeros. We know that any number ending in a 0 will have a factor of 10. But in case of perfect square numbers, the factors have to be in pairs. Each pair will be resulting in 2 zeros. So multiple pairs of the factor 10 will give either 2, 4, 6 or other even numbers of zeros. So that means a perfect square number, if it ends with a 0, has to have an even number of zeros. But here again, not all the numbers which have even number of zeros will be perfect squares. For example, 30,000 has 4 zeros, but it is not a perfect square. Similarly, 1700 has 2 zeros, but it is not a perfect square. The next property. Squares of even numbers are always even and the squares of odd numbers are always odd. Here again, let's check the table of first few square numbers. If you notice, all the odd numbers when squared result in an odd number, and all the even numbers on squaring will result in a perfect square which is even. With that, we'll move on to the next property. A perfect square number leaves a remainder of 0 or 1 when divided by 3. As usual, let's check the first 10 perfect square numbers. On dividing each of them by 3, we get these quotients and remainders. Though the quotients are different, the remainders are always 1 or 0. This means any perfect square number when divided by 3 cannot have a remainder of 2. But we'll again remember that all the numbers which leave a remainder of 0 or 1 on dividing by 3 will not be perfect square numbers. For example, when you divide 33 by 3, it gives a quotient of 11 and a remainder of 0. But still, 33 is not a perfect square number. Similarly, 46 when divided by 3 leaves a remainder of 1. But still, 46 also is not a perfect square number. The next property is quite similar. A perfect square number leaves a remainder of 0 or 1 when divided by 4 as well. To check this, let's take the first set of perfect square numbers. On dividing by 4, we get these quotients and remainders. A remainder of either 1 or 0. You can also see that the remainders alternate between 0 and 1. Whenever the number is even, the remainder will be 0. And when it is odd, the remainder is 1. So, any perfect square number when divided by 4 will not have a remainder of 2 or 3. But not all numbers that leave a remainder of 0 or 1 when divided by 4 are all not always perfect square numbers. For example, let's consider 85 and 44. When dividing these two numbers by 4, we get a remainder of 1 and 0. But these two are not perfect square numbers. With that, we move on to the next property. The difference of squares of two consecutive natural numbers is equal to their sum. Let's consider two consecutive natural numbers, 4 and 5. Now, let's take 4 squared. We'll represent this as a large square with 16 smaller squares. Now, when you add 4 small squares and 5 small squares. What happens is you get a total of 25 small squares, which is nothing but 5 squared. These two are the two consecutive numbers, and when you find the difference of their squares, we have the sum of these two numbers. This is true for any two consecutive natural numbers. Let's check some more examples arithmetically. 7 squared minus 6 squared is 49 minus 36, which is 13, and 13 is 7 plus 6. 11 squared minus 10 squared. This is 121 minus 100, which is 21, and that is also 11 plus 10. Let's check why this is true. If n and n plus 1 are the two consecutive numbers, on squaring we have n squared and n plus 1 the whole squared. Now finding the difference. N plus 1 the whole squared can be expanded as n squared plus 2n plus 1, and we'll subtract n squared from this. What results is 2n plus 1. This can be written as n plus 1. These two are our original consecutive numbers. Now we'll move on to the next property. The square of a number n is equal to the sum of the first n odd natural numbers. Let's understand this property also visually. First, let's take 1 squared, which is 1. The next odd number is 3. So when you add 3 small squares to this 1 square, you get a total of 4 small squares, which is 2 square. 2 square is the sum of first two odd numbers 1 and 3. Next, let's take the next odd number 5. So we'll add 5 small squares. What results is a total of 9 squares, which is 3 squared. 3 squared is the sum of first 3 odd numbers 1 plus 3 plus 5. Similarly, when you add 7 to this, you will get a total of 16 small squares, which is 4 squared. And then you add 9 squares to make it 25 small squares, which is 5 squared. This pattern keeps continuing. So, for any number n, when you square it, it will be equal to the sum of the first n odd numbers. With that, we come to the last property. For any natural number m which is greater than 1, there exists a Pythagorean triplet 2m, m squared minus 1 and m squared plus 1. A Pythagorean triplet is a set of 3 numbers a, b, c, where a squared plus b squared is equal to c squared. These 3 numbers are sides of a right triangle. The square of the largest side, the hypotenuse, is equal to the sum of squares of the other 2 sides. According to our property, we have a is 2m, b is m squared minus 1 and c is m squared plus 1. On squaring, we have a squared is equal to 2m the whole squared, which is 4m squared. b squared is m squared minus 1 the whole squared, which becomes m to the power of 4 minus 2m squared plus 1. Now adding these both, we have 4m squared plus m to the power of 4 minus 2m squared plus 1, which is m to the power of 4 plus 2m squared plus 1. This is nothing but m squared plus 1 the whole squared. In our case, c squared. Thus, the three numbers represented by 2m, m squared minus 1 and m squared plus 1 will always form a Pythagorean triplet. For example, let's take m is equal to 2. We then have 2 into 2, 2 squared minus 1 and 2 squared plus 1, which becomes 4, 4 minus 1 and 4 plus 1. That is 4, 3 and 5. Now let's square them and check. 4 squared plus 3 squared should be equal to 5 squared. 16 plus 9 should be 25. 25 is equal to 25. Hence, we conclude that the given set is a Pythagorean triplet. Hope this video has helped you understand properties of perfect square numbers. If it did, give it a like and share it with your friends. Thanks for watching.